All right, just let me know if you can't hear me. Let me double check, make sure I'm not muted. Nope, I am not muted. Okay. So today the lecture will be on geologic origins. There's a question about is there a camera requirement or anything that you have to do to get attendance credit on Top Hat? I don't have a camera requirement for this class at all, not even for your exams. The exams won't be proctored. To get credit for being in class, you'll have to answer the quiz questions. So I have quiz questions at some point within the lecture. You get partial credit just for trying to answer them. That's kind of like your attendance credit, and then additional credit for getting it correct. I also have in-class assignments that I'm assigning participation points for. So that's kind of how I'm incentivizing you all coming to class. Okay, so today we'll be covering the formation of the Gulf of Mexico, the formation of Florida and the Yucatan Peninsula, how we measure seafloor spreading, the formation of major bathymetric features, and how other coastal features around the world are formed. I really like that view, so I'm just going to stop sharing my screen through Top Hat. Okay. The learning goals for today are to understand that the Gulf of Mexico was formed by tectonic activity when the supercontinent Pangaea broke up, to learn that seafloor spreading rates can be determined by dating magnetic anomaly stripes of rock on the seabed, and that the Gulf of Mexico has some of the most interesting bathymetry out of all of the world's coastal features, and we'll learn a little bit about that. We'll learn that the largest seas, gulfs, and bays of the world were formed by tectonic activity, but fjords and drowned river valleys have different origin stories. And this image here is just to remind you that since we're talking about the Gulf of Mexico, and LSU is probably the preeminent place for experts on the Gulf of Mexico to go to study, we do have a lot of folks at LSU that are at the forefront of a lot of the research that I'll be talking to you about during this course. So this here is a picture of LSU professor Christine DeLong and her graduate student trying to study a coral reef fossil from the Gulf of Mexico from about 120,000 years ago. So today I'll be asking for some feedback from you all. Many of you were in my Intro to Oceanography class, and so I know what you covered during Intro to Oceanography, but there are plenty of you that did not take Intro to Oceanography with me, and so I want to make sure that we're all on the same page. So periodically throughout the course, including during this lecture, I'm going to do kind of like a spot check. I'm going to highlight some terms that I think that you probably covered in Intro to Oceanography in blue throughout the lecture. I have a discussion open in Top Hat, and I want you to let me know if there are any of those terms in blue that you have not seen, or anything else in this lecture that I don't explain that you need more information on. So that will help me figure out where we all are. Even if you think you covered it but you don't really remember it, you can let me know that too. And as always, just ask questions if you want me to go into more detail on something throughout the lecture. To get to that discussion, what you'll have to do is in your Top Hat, when I'm presenting a virtual classroom, there should be a tab somewhere in the top of the screen, I think it's in your top left, that says Assigned. And so if you go to that tab, you're able to access the different course content that I've assigned for this class period. You'll get to access the whole course tree, week 1, week 2, so on and so forth. And so in today's folder, you will see a discussion that should be active where you can share. You are not required to respond to this discussion. So don't feel like you have to. Also, in the assigned material for today, I have included a file, a PowerPoint file of this class's PowerPoint slides. In case you like to go through and take notes on those, those are going to be available now before class on Top Hat, so you can print them out if you want, if that's your thing. Alrighty. So, into the content. So today we're going to try and understand how the Gulf of Mexico formed and how other coastal features formed. The Gulf of Mexico was formed by tectonic activity is basically the punchline there. So the Gulf was once part, as are all land masses, anything that wasn't formed by volcanic activity, it was part of the supercontinent Pangaea, 175 to 355 million years ago. And so million years ago is going to be denoted throughout this talk as MA. That's million years ago. And so you can see as the continent started to break up, here is a red box around what would become the Gulf of Mexico. And eventually it ends up in its present day form. When the Gulf of Mexico was in Pangaea, it was land located south of a mountain range extending from central Mexico to the Appalachian Mountains. So it wasn't really part of the mountain range, but it was nearby. There were rifts in Pangaea that began creating all the continents, including the Gulf of Mexico, around 200 million years ago. And a rift is an opening or a crack in tectonic plates as they move along the Earth's crust. A 6,000 kilometer long crack, a rift, split Pangaea into two supercontinents. So we have Laurentia, which is most of what's now North America, and you can see here also Asia, and Gondwana, which is South America and Africa today. So you can see the Gulf of Mexico was a part of that rift that essentially separated those two supercontinents. And rifting is something that we can see today. It's a very common way for new land masses to separate and form. It's how oceans form and grow. So rifting and then the process of land masses spreading apart is how we get oceans. It happens when a hot spot develops underneath the continental lithosphere. And so that hot spot pushes up material into the crust and allows the crust to begin to pull apart. And you get faults occurring in the crust. And faults are fractures or a series of fractures in the crust that allow a rift to form. And so in this image, a fault would be indicated by these upward jagged looking lines. Those would be indicative of a crack forming. And then a new ocean basin opens up eventually because you have a low spot now where that rift formed and allows seawater to enter. And just because seawater enters a new ocean basin one time doesn't mean it's going to be open to the ocean forever. These ocean basins have a way of opening up and closing up, allowing seawater to enter at different points in their history. And sometimes when these are closed up, the water will evaporate and it'll leave behind salt deposits. And so that's a very normal process of a new ocean forming. It's not always underwater. Finally, when that rift gets large enough and the opening is always open, you get a mature ocean forming, and that allows for seawater flow and it allows for sediments to accumulate in the mature ocean. So this is essentially the process by which an ocean is formed. We have examples of various stages in this process in today's world. So we're able to actually see how this plays out in our geology. So for instance, we have a very great example of a rift valley, and that is the African Rift Valley. And you can see the African Rift Valley here. There are a variety of these like long lake-like features. So these will be forming in rifts. So the African Rift Valley is made up of many different rifts and faults stretching from Lebanon in Asia to Mozambique, which is in Southeast Africa. All of the African Great Lakes were formed as a result of this rifting. And as of right now, in this area, there's no opening to the ocean. But as you know, that is a stage of forming an ocean. So eventually, these will form new ocean basins, and those African Great Lakes will form seas, and eventually a new ocean over geologic time. Now, the Red Sea would be considered a new ocean basin. So here's the Red Sea here. This was formed by the divergence between the African plate and the Arabian plate. And it was once a rift valley, but now it is connected to the Indian Ocean. You can see it's connected here. It's one of the saltiest bodies of water in the world. So there's very high evaporation. It's in the desert, so there's not a whole lot of precipitation. There's no major rivers feeding into it. This was formed by tectonic activity, not by any sort of riverine activity. So it's very salty. And it's able to support really, really high biological diversity. So it has around 2,000 kilometers of coral reefs that support a lot of diversity in this region. So it's extra special to marine biology. So this would be an example of a new ocean basin. And eventually, as this rift spreads wide enough, this will be open to the ocean all of the time. That extra salinity, the extra saltiness will go away because it will just be an extension of the Indian Ocean. And then eventually it'll form its own ocean. So here I have some more advanced material covering the formation of the Gulf of Mexico. This is going to be an example of honors material here. So I'm showing you the process of the creation of the Gulf of Mexico here, and we're going to follow this cross section between South America and North America. So this is not the location of the rift, this is the cross section that we're going to be looking at. And here you can see at various points in time what that cross section looked like. So we would have here the South American continent and here the North American continent. So step one in formation of the Gulf of Mexico was rifting. So these plates began to pull apart. There was a hot spot that formed that started to fill in continental crust material with some oceanic crust, some brand new crust material. So we had an ocean forming. And then in the second step, we had a seafloor forming and spreading. So we had early North Atlantic seafloor spreading happening. So this thinner crust here denotes oceanic crust. You can see now that's separating the continental crust. And we have this little bit over here of some thinner continental crust, adjacent to the new ocean that's forming. And this thinner continental crust is going to be the location of the Gulf of Mexico. In step three, as the seafloor spreads, the material has to have somewhere to go. And so what you end up getting is a subduction zone forming, where that plate slides beneath the continental crust. And then you have an area in the middle of Gulf of Mexico that becomes a hot spot as this crust ends up melting and the magma seeps to the surface. And so you actually get seafloor spreading in the Gulf of Mexico, making it larger. In step four, you have an additional hot spot forming here, which makes the Caribbean islands. And the Gulf of Mexico, you can see, is larger than it was initially. It's spreading. There is a basin here. And then finally, at the end, we get stability, where the subduction ends. All of this material, this crust material, ends up melting. There's no more spreading in the Gulf of Mexico. The Caribbean islands are no longer a hot spot, and we get stability, a fully formed Gulf of Mexico. You can see that there's still some spreading in the Caribbean basin, but the Gulf of Mexico is no longer experiencing seafloor spreading. So the Y in this bottom image is for the Yucatan Peninsula. And there's a little bit of a special way that the Yucatan Peninsula formed. So I want to go over that now. You can see through most of its history, the Yucatan Peninsula was a piece of somewhat thinner continental crust, but it has some unique history as to that make it what it is today. So we'll go over that next. So this is material for everybody again. So the Yucatan platform was not actually covered with water until about 100 million years ago. So relatively recently, it started to be submerged. And by the platform, I mean not just the Yucatan Peninsula that we see today, but this entire shelf. That's what I'm talking about. And so that whole platform was above water until about 100 million years ago. And then it became covered in water and it became a shallow sea. And in shallow seas and relatively tropical areas, we get a lot of biological activity. We get coral reefs forming, we get a lot of sea life, we get algae blooms. Shallow seas are very productive. And so what ends up happening is carbonates accumulate. And carbonates are made of biogenic sediment, so sediment that's made of living creatures, specifically creatures made of calcium carbonate. And so they have calcium carbonate shells. This would be things like bivalves, so like clams, oysters, things like coral reef shell material. And so all of these would contribute to the growth of this platform. Over geologic times, this is over a long period of time, all of that material accumulates and a platform of carbonate material forms. And the Yucatan carbonate platform is quite thick. It's 2 kilometers thick. So that's 2 kilometers of biological activity contributing to building up that platform, keeping up with sea level rise over time. And so you can see here, over geologic time, over tens of thousands of years, how a carbonate platform can fill in as sea level rises over time. That biological activity is able to keep up and to keep the platform as a shallow sea kind of environment. The Florida platform is also a carbonate platform, at least partially. So as the rift was forming, the rift that ended up making the Gulf of Mexico, there were actually a number of smaller rifts that formed that created low valleys. And one of them was across the Florida Panhandle and into Georgia. And this rift and eventual valley that formed was called the Georgia Seaway. And so what the Georgia Seaway did is it kind of separated the Florida platform from all of the rivers and all of the geology that was happening on the continent of North America. Separated it from North America, so all of that riverine input didn't end up putting sediment on the Florida platform. The Florida platform was left alone in clear, pristine waters, in shallow tropical seas, and so we get the same kind of thing happening as in Yucatan, where you get a lot of coral reefs, a lot of biological activity, and carbonate sediments accumulate in great abundance in Florida, creating that carbonate platform. The Bahamas were also formed as a carbonate platform, and the Bahamas, that carbonate is around 8 kilometers thick under the Bahamas. So it's a lot of biological activity that created those islands. Pretty cool to think that biology can create these giant geological masses over time. Coral reefs are pretty cool. Any questions about the formation of the Gulf of Mexico? Okay, I want to talk about how we know all of this. So There are a few steps, a few lines of evidence that we can use to understand how land masses were formed, where land masses went as they moved across the Earth's surface. The first is we take samples, and so these samples are in a couple of different forms. We can use robots to take rocks from outcroppings, and so if we have, for instance, this is like a vent system, there might be some rocks that a robot with arms could collect from such an area. And we take cores from drilling into the crust. And so these are cores that specialized ships can take. And they drill not only through the sediments, but also into the ocean, the rock material, the oceanic crust material. And you can also take sediment cores so you can understand where the sediments came from. And if you're interested in any of these processes, I have on your lecture slides that you can download, I have 3 links of videos here. The video of the core of the drill that actually does oceanic coring is pretty cool. We can understand seafloor movement. So where seafloor has been, the pathway it took to get to where it is now, the pathway the continents took to get to where they are now. We can understand that by looking at the polarity of rocks. And so that's what we'll talk about next. I wanted to mention that there are these really large libraries of rock material from oceanic crust that are stored throughout the world. And these have extremely valuable information for geologists and people trying to understand the geological history of Earth. And one of them is at Columbia University in New York City. There are thousands of cores there, and I thought this picture was pretty cool, like a library of crust and sediment cores. I'd love to see that. All right, let's talk about magnetic pole reversal, because this is where we're going when we're trying to understand seafloor spreading. And I know that most of you have probably had an introduction into this several times. Hopefully there's some new information for you here, but I think it's worth revisiting. So the Earth's magnetic field flips occasionally. The North and South Pole will flip occasionally. The reasons for this are not extremely well understood, but it probably has to do with differences in patterns of convection in the Earth's outer core. That's the thought so far. The major theory revolving around the magnetic field flipping. How common are these magnetic pole reversals? Well, first of all, it's important to know that they're random, so they don't really occur at any specific schedule. But if we look over geological time, they tend to occur about 1 every 500,000 years. There's a lot of wiggle room there because, as I mentioned, they're random. The latest flip occurred almost 800,000 years ago. So you might say that we're overdue, but again, remember, these are random flips. And they're not immediate. I mean, if you think about geological history, they occur quite quickly, but in terms of human history, they're actually quite slow flips. So the time it takes for a reversal to complete is around 7,000 years. So it's not just like you're gonna wake up one day and, north is south and south is north. This would happen over many, 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 many human generations. So not anything to stress about. When the seafloor is forming, the rocks that are forming at the ridge crest, so right in the middle, brand new rocks that are forming, record the magnetism existing at the time they solidify. And so the different materials in the rock will line up to show, essentially point and according to the magnetism at that time. So we can see how these strips of magnetic material move throughout the world's oceans, and that can give us an idea of how things, how that rock material moved over time. The seafloor will increase in age, even though it'll hold its polarity, and it will become more deeply buried by sediment as it moves further away from where it was formed, because sediments will have longer and longer time to collect there because it's older. And we can go ahead and take a look at where these seafloor magnetic anomaly strips lie. We can take dates, we can carbon date them, so we can figure out approximately when they were formed. And if we track them over space and measure their distance from the ridge crest or the new rock that's forming, we can figure out how these different plates move and how that material has moved over time. So it's a few different steps to get there. First of all, we need to go ahead and map the location of those magnetic anomaly strips. Second, we need to date the material. And third, we need to measure the distance between the material and the ridge crest. And that can actually give us a pathway that that material is spread over time. So this is how we know where the continents were and how they got where they are now. Any questions on that? You want a few more minutes? Okay, that's fine. Thanks for the feedback. It's good to know. It's hard to judge when I can't see you all. Okay, so since the end of the Gulf seafloor spreading that we talked about, the size of the basin of the Gulf of Mexico basin has been relatively stable. We don't really have seafloor spreading going on. The Gulf of Mexico is not expanding. But what has changed is that sea level has changed. So the sea level has gone up and down since the Gulf of Mexico was fully formed, changing the shoreline. And the ways that we know how this happened are we can look at salt deposits, and that tells us the maximum water extent. So this image here is showing you salt deposits that depict an earlier shoreline during a sea level maxima. And so you can see the shoreline really, all of Louisiana was essentially underwater. We have a shoreline up into Arkansas. We have a shoreline extending up into Georgia. All of Florida was underwater. And then if we want to know the minimum water extent, then we have to look at the location of the continental shelf. So the continental shelf tells us how small the Gulf of Mexico has been. And so you can see the location of the continental shelf, Florida, for instance, being a lot larger during a sea level minimum. Same with the Yucatan Peninsula. So the surface area of the basin does change as the shoreline moves. And that's not due to tectonic activity, that's due to changing sea level. So I have a activity here. So this is called a page. This is a little bit different from the slides that I share. Are you able to see this as I bring it up here to present? You're still seeing the slide. Okay. So what I want you to do is to do a activity. Go into your assigned content. And I'm going to assign a activity called Human Connections, the Black Belt. Are you able to see that now? Great, thank you so much. I appreciate you letting me know. Excellent. Okay, so take a few minutes. I'm going to give you about 10 minutes to go through this activity. It's a little bit to read and then a couple of questions. And the goal for this activity is to get you prepared for your current event assignment. So the questions that I'm asking here are very similar to the types of questions I want you to answer for your current events. So this will be practice. And I'm going to leave this open as homework, and it'll be due before class on Wednesday of next week. The name of the assignment, so it's going to be under week 1, 3 in class, and the assignment is Human Connections, the Black Belt. I don't expect you to complete it now. You'll have it as homework, but I'm going to give you 10 minutes to work on it, so that way you can ask me questions about what you see. Excellent. Thanks, Peyton. Mariah asked, if we don't submit the answer and we exit the class, does it save what we have written so far? I actually don't know the answer to that. So my suggestion would be to go ahead and submit it, and you can have another go at it. I'll just make sure that that's an option. You have unlimited attempts per question. You bet. And if it gives you any grief, just let me know and I'll make sure you get your points. This is something new that I have not tried out yet, so. Okay, I'm going to start sharing slides again. Up top in the same tab where you went to access your assigned material, you will see just to the left of that a way to get back to the virtual classroom. I think the tab is classroom or something like that, where you can get back to where I'm sharing slides. So let's talk about the formation of other large coastal features. Many of the largest seas, gulfs, and bays of the world were formed in a very similar manner to the Gulf of Mexico. And that is that as Pangea broke up along curved and indented fault lines, the continents moved apart and they left these large indentations that are now bays or gulfs. So this is true of the Bay of Bengal. It's also true of the Gulf of Guinea. So here we're looking at near India, the Bay of Bengal, and the Gulf of Guinea being basically in the little like armpit of Africa. There are many coastal features that are still being formed today by tectonic activity. So we talked about, for instance, the Red Sea. And if you want to know if a coastal feature is being formed by tectonic activity, the best way to do so is to look for fault lines that might provide origin story clues. So you'd be looking at a geological map that shows where fault lines are, and if they align with whatever coastal feature you're looking at, odds are it was formed by tectonic activity. Fjords are formed in a different way. They're formed by glaciers. So fjords form because glaciers tend to form in the valleys of mountain ranges. And as those glaciers melt, they erode the valley and they carve out a deeper valley that eventually is filled in with water, and that's a fjord. The fjord is often deeper than the surrounding sea itself. So these are quite deep features. And one telling feature that you can, well, first of all, they're surrounded by mountains. So they're valleys between mountains, which is a great way to tell that you're looking at a fjord. But you can also look for these features called moraines. And this is where rocks are deposited at the seaward side of the fjord, essentially at the area where the glacier ended. You get this rock bar forming that creates a sort of sill. And that's because as the glaciers melt, they actually deposit debris in this area, and then the meltwater will run off, but a lot of the debris gets left behind. And so this is essentially a glacier waste heap in the moraine. So you can see a very, very deep feature in this dark blue here. and this lighter orangey red feature would be the moraine or the glacial debris deposit. My favorite fjord is the Sognefjord. This is in Norway. This fjord is my favorite, and I give it as an example here because it's my ancestral home. So I actually got to visit it a few years ago. So these are pictures that I took in the area around the fjord. It's also geologically unique, so it's a good example to show you what a fjord is like. It's very long and deep, so it stretches more than 200 kilometers inland. So it's essentially, it looks kind of like a river, right? But it's not. It's actually a valley, a flooded valley that's been carved out very deeply. All of this dark blue that you see here are areas that are extremely deep. It has a maximum depth of 1,300 meters. So a pretty cool fjord. I don't know why my ancestors left, but I'm just glad I got to see it. So moving on from tectonic activity, from fjord formation, now we're going to look at a drowned river valley formation. And so I think the best example of a drowned river valley forming would be the Chesapeake Bay. And I alluded to the fact that the Chesapeake Bay was formed by a meteor strike in previous lectures. So let's talk about how that happened. So about 35.5 million years ago, a meteor collided with Earth and formed a massive crater. This actually happened offshore on the continental shelf, what was then the continental shelf. And here's the location. Here is the approximate location of the shore at the time the meteor was impacting the Earth. The depression created by the crater caused river valleys to converge. So rivers actually changed their direction and started flowing to this area of this lower area. So river valleys started to flow together. Millions of years later, sea level actually fell further, and the rivers carved a deep canyon on their way to the Atlantic Ocean. And so that canyon flowed right through here where you see water today. And then over time, sea level started to rise again about 10,000 years ago and flooded the river valley. So that deep canyon that had formed was then flooded, and it formed the bay that we see today. And so we call this a drowned river valley. It's exactly like it sounds. It was a river valley, and when rising sea levels came in, that river valley was flooded, and so now it's a mix of saltwater and freshwater permanently. But you still have lots of rivers flowing in there. So you can see a river flowing through there. There's a river that comes in through Baltimore. So drowned river valleys are formed when rising sea levels flood existing river valleys. First, we had the meteor strike. We had rivers converge. They carved out a canyon, and then that canyon was flooded. The Mediterranean Sea is another example I wanted to give you. The sea was formed by tectonic activity, but it's not quite like the Red Sea because the Red Sea is forming, it's spreading, but the Mediterranean Sea is closing up. And so the Eurasian and Arabian plates are coming together in this location. Over time, over geological time, it's actually closed up completely and reopened many times. And perhaps the most interesting event in its geological history is the Zanclean flood, which happened only a measly 5.3 million years ago. And that was when the Strait of Gibraltar was completely shut, but it opened and flooded the Mediterranean Sea. It was an amazing event. It happened very quickly, over months to years. And the Mediterranean water level rose 10 meters per day. That's a huge amount of water. And it actually was so much water being put into the Mediterranean basin that the global sea level decreased by 10 meters throughout the course of this event happening. That's pretty cool. If you wanted to watch a video of an artist rendering of what that would have looked like, I have a link here. And this is honors material, but I think it's cool for everybody. In the last few minutes, I'm just going to give you your quiz. There are 2 questions for the quiz today. So go ahead and make sure you're on top hat. The first quiz question, match the following origins to the photos of coastal features, and the letters are going to be A, B, and C in these photos. So A is what looks like this river that expands as it moves towards the ocean. B is this glacier at the top part of this water feature that's between some mountains. And then C, this is a geological map showing some faults around the Bay of Biscay. And your answers you have to match are drowned river, glacial activity, or tectonic activity. Make sure you hit the submit button when you're submitting your answers. And in the interest of time, I'm going to make this the only quiz question for today. I don't want to keep you guys over. So we'll end class after this. Looks like I have one person who hasn't hit submit yet, so let me know if you need more time. Otherwise, I'm going to show the correct answers here soon. There we go. Okay, cool. So the first one, A, was a drowned river valley. The second one was formed as a fjord through glacial activity. So we saw the evidence of a glacier there, so that was our clue. And the third one, because we have so many fault lines showing in this image, the Bay of Biscay is formed through tectonic activity. So very nice job. All right, so we're going to go ahead and end class there. And next class is going to be on, what is it? Let's see. So Monday's class is canceled. It's Martin Luther King Day. And so I'll see you on Wednesday and we'll talk about the Gulf Stream. So have a wonderful long weekend. And don't forget to complete that Human Connections assignment as homework. Yep, see you Wednesday. Take care.